Welcome and thank you for joining us today for Proactively Building Competitive Advantage, Mastering Business with the Speed of In-Memory Computing. My name is Raleigh Gould and I'll be your moderator for today's event. Our featured speakers are John Myers, Managing Research Director at Enterprise Management Associates, and Nikita Ivanov, Founder and CTO at GridGain. In his role as Managing Research Director of the Business Intelligence Practice Area, John delivers comprehensive coverage of the BI and data warehouse industry with a focus on database management, data integration, data visualization, and process management solutions. Nikita has over 20 years of experience in software application development, building HPC and middleware platforms, contributing to the efforts of organizations including Adaptec, Visa, and BEA systems. At GridGain, he has led the company to develop advanced and distributed in-memory data processing technologies. And I would like to go ahead and turn things over to our first featured speaker, John Myers. John?
Well, thank you very much, Raleigh. I appreciate that nice introduction you gave for us. Today what we're going to do is we're going to talk a little bit about the importance of speed of response, which is what the technology of in-memory processing really provides to us. We're going to talk a little bit about some industry use cases associated with in-memory and how it handles it, and then we're going to hear from Nikita and how GridGain addresses these particular issues with their solution. So, some of the most important disruptive forces in data management is changing that overall speed of business. And one of the examples I like to give is how in different domains we've sometimes accepted a particular speed, but then when someone brought us a new piece of technology or a new development that allowed us to kind of break through to a new area, we really found improvements in those particular areas. If we kind of go around the corner, around the screen here, we originally thought that ships could only go from point A to point B by being able to see land, but then somebody invented the sextant and allowed people to go not just around the oceans, but to go through the oceans to get there from point A to point B. In terms of the airplane, we once thought that prop-driven aircraft were the limit, the theoretical limit that was available to us. In fact, you know, if you've ever seen the movie The Right Stuff, they always described it as the sound barrier was a brick wall in the sky that would prevent you from going any faster, until we figured out that we could go faster than the speed of sound, and now we have all sorts of interesting applications, including spaceflight, that come from that ability to break through that particular barrier. If we look in the upper right-hand corner, we once thought computers and things of that nature needed to be in large rooms for very to have it be managed in an IT environment. But then along comes somebody and says, hey, let's put a computer on everyone's desk and let's see how they can make use of those particular abilities. And then in terms of photography, we used to have photochemical processes associated with the camera that you see in the middle, but now since we've gone to an electronic-based or a digital-based photography, we now have things where we can get very high-quality videos, movies, etc., anything we want off of our cell phones. That being a flip phone is probably an old example, but thought I'd throw that in there. But in each of these cases, we had a situation where we thought, okay, we've reached the end of a particular technology. We kind of have to accept some of the limits associated with that, but people helped us break through those limits and find new applications, new uses, new ways of looking at things, and being able to break free in each of those particular areas. In terms of breaking the speed of sound for applications, whether they be analytical or operational, I found some of the technologies that are really making that possible are, on the first hand, MPP compute models, being able to distribute across a large number of nodes to be able to, instead of just going through one particular platform where we're scaling up into one box, but being able to scale across our processing models across multiple platforms. Multi-structured data and late binding schemas, the ability to say, let's not wait to start our ingestion of data until we have a perfect data model, but in terms of being able to accept multiple schemas and data models that allow us to get where we're going. And then, of course, in-memory processing, the ability that instead of constantly going to some form of spinning disk, that we are able to manage our processing in memory using the processing power that we have and the available memory that we've got. This allows us to maintain massive amounts of data in a reasonable amount of time. We've always been able to do large amounts of data, but oftentimes when we hit the button, we would kind of go away and say, all right, I'll go get some coffee, or I'll let the job run overnight, or things of that nature. With in-memory processing, we're able to do massive amounts of data in almost real time. I always shy away from the term real time, but in-memory processing is allowing us to do things in a response time that average business users, when they hit the return key, they're able to say, oh, now I'm seeing my results, or I'm starting to see my results, instead of having to wait. We're able to look at a broader set of data in a real-time environment, or as I said, a near real-time environment, where we're able to, instead of just looking down one particular degree path or one particular domain, we're able to say, let me see some from customers, some from products, some from region, information that we haven't brought into the system before, and to be able to bring that together. And then these particular concepts also allow us to iterate or fail faster in whatever it is we're doing. Oftentimes, if it takes a long amount of time to do an analytical process or an operational process, we'll be very cautious in how we apply it or how we execute it. Being able to go faster with MPP, with multi-structured data, with in-memory processing, allows us to take a look at a particular workload, execute it, look at the results in near real time, and go, okay, these are the things we like, these are the things that we don't like, make adjustments, and then continue to iterate through that at a much faster pace than we may have before. This allows people who are business analysts, people who are developing particular models or particular operational workflows, to be able to see what are the challenges before them, identify those challenges, fix them, and then continue through the process. So instead of saying, okay, I'm going to run my job and it'll take me an hour to come back or 15 minutes to come back, I can hit the job, see my results, make an adjustment, and then continue down that particular path. Speed of response is also very important with end users. In a recent EMA study where we took a look at next generation data management platforms, we asked what were the use cases that folks were using associated with those platforms. The number one use case by far was speed of processing response, being able to identify how we're going to run our workloads and make sure we get that information as fast as humanly possible. This goes to a lot of components where we take a look at when we try to build competitive advantage in our organizations, to be able to say, as we're executing on these jobs, how do we get them out as fast as possible, or how do we integrate them in with our operational workflows? How do we get those particular pieces to move down the pipe? In terms of in-memory processing, we've had in-memory processing for many, many years. I mean, if you look at the established academic research and you look up in-memory database processing or in-memory processing, you'll find that, this goes back to the 1980s and set-top boxes, when you couldn't put a spinning disk on a remote device. You had to put everything in memory and you'd operate it in that particular fashion. But those were very limited use cases. Oftentimes, if you wanted to use them, they were very expensive to do so, because the cost of memory was very high. The capacity of platforms to hold memory was relatively low. So it took a lot of time, trouble, effort, and resources to get a particular memory implementation to go. What we've seen over the last couple of years, and specifically over the last 2 to 3 years, is where I consider to be a tipping point in terms of both the capacity and price of memory associated with platforms. We're seeing hardware manufacturers putting larger and larger capacities of memory in servers. We're also seeing the price to fill those memory slots come down considerably. What this does is it makes sure that you can take the business cases associated with in-memory processing. And instead of it being highly targeted, very high value types of business cases, it allows you to move down the path and say, how do we open this up to a wider range of business cases? So just as in-memory is allowing us to break through in some of the analytical models that we're looking at, these falling prices associated with memory and the increased capacity associated with these memory spaces allows us to open up the door to a wider range of options to handle that. If you take a look at the continuum of in-memory processing, we go all the way from an all-in-memory solution, which means there's virtually no spinning disk anywhere associated with a particular in-memory processing platform or a database or things of that nature, and everything is maintained in memory. There are a majority of in-memory where you are only using spinning disk as part of a disaster recovery or a durability component associated with your processing, whether that be operational or analytical. You can flip that over and you can say, let's just use in-memory to do particular workloads associated with what we're taking a look at, but a majority of our information will be stored on spinning disk. Or you can talk about no in-memory, where you have everything associated with spinning disk. But when we talk about the continuum of in-memory processing, we go all the way from, everything is in memory, everything's going to be cached in a memory environment, all the way down to a point where we literally aren't using much of anything at all. Only the processing aspects are maintained in memory, and then everything is returned to the spinning disk as we take a look at that. In terms of use cases, how would I use an in-memory solution? What type of value would this bring to me in my organization? One of the keys and one of the pioneers of in-memory processing has always been the financial services industry. For many, many years, high-frequency trading, algorithms, things of that nature have depended upon in-memory processing models. Those were very specific, very, if I want to be so bold as to say, you had to have a lot of money to want to go that fast, and trading was one of those particular areas. But as we move into new areas that are enabled by in-memory capacity processing, things of that nature, and we look at the lowering price, we can now move from saying it's just going to be something we look at for trading. It's going to be something that we're going to take a look at to see how do we manage our regulatory environments and how do we achieve some competitive advantage on those regulatory environments. And I'll give you an example. So if you've been following the financial services industry over the last couple of years, there have been a number of significant regulatory components that have come down the pipe. These include the Dodd-Frank Act, Basel I, II, and III, Sarbanes-Oxley, et cetera. Included in those requirements are large amounts of regulatory reporting constraints. So financial services organizations need to be able to return information on a relatively fast basis to make sure that they are in regulatory compliance. But if we were to take that regulatory compliance obligation and enable it with in-memory processing, we would be able to say, how do we, instead of looking at a quarterly liquidity risk where we're asked from our regulator, we could say, give me a daily, an hourly, an almost in real-time evaluation of our liquidity risk associated with our position. And how do we take that position that we now have over a competitive advantage that we now have over our others in the market who may be stuck at that quarterly rate because they can't go any faster? How do we make trades that would allow us to take advantage of their lack of knowledge of the market? How do we take a look at our own liquidity risk and say, we've extended ourselves too far, we need to pull back and rebalance, almost, again, in an intraday, real-time type of environment. But to be able to pull all the information about the assets that we have in a financial services organization, look at where we are from a risk perspective, driving that report to meet the regulatory requirement, but take the timing of it and move it up and increase the speed of it much more effectively. In terms of retailing, there's a concept out there called omni-channel retailing. And this is the concept of being able to say, how do we fully integrate our bricks and mortar with our online presence along with our supply chain environment? At the very basic point, you could say, let's make sure that we take our supply chain and our pricing and match them to individual store demands that we may project for, say, the New York area or Des Moines, Iowa, or for Denver, Colorado. In each of these particular instances, we can take historical information. We can take a look at what those goals were, those demands were, make estimates, tune our supply chain to bring that information together. In each of those areas, we're looking at pricing in one area, demand in one area, and supply chain in another area. But imagine we were to bring all of those components together so that we could say, based on our distribution areas, based on demands that we have at stores in relative real time, how do we align our supply chain to make sure that we don't have a stack or a pallet of one of our most popular product items or most demanded items in an area where we have little or no need for it, what we have lines out the door at a different location. How do we bring those disparate data sets together so that we can say, let's align our supply chain and our distribution and possibly even align our pricing to say, instead of having to give discounts to move product in those areas where we have too much, align that product delivery to where it needs to be with the demand so we can maximize our prices, meet our customer demand, and satisfy our customer base all at the same time. In-memory processing now allows us to do this because we are taking information from this broad set of data sources, and where we might have been looking at it to say, let's meet just minimal critical needs based on projections, we can now say, based on information that's associated with individual store demands, individual customer demands, whether that be online or in a particular physical store, match those up and get delivery of those options in a relatively short amount of time. In terms of utilities, in-memory is providing the opportunity to really enable a concept we've heard of quite a lot about over the last couple of years called smart grid. It's one thing to collect data from all the different points along a particular utility grid, whether that be electrical, water, et cetera. But it's something else to be able to say, how do we pull all that information together and take a look at it in terms of some of the most important constraints that we have, which are oftentimes a real-time constraint, which is weather. For example, there was an issue last year where in Germany, which has a very highly regulated utilities market, where because it was a sunny day, it was a cool day, and it was a windy day, they were able to maximize their solar components. They were able to generate quite a bit of electricity from their wind turbine constraints, and they actually didn't need many of their other types of power generation online, but because of the way the grid is aligned, they needed to have those components up and running, which caused an oversupply of energy on this particular grid. On the course of the day, they actually went to the point where they were paying people to take electricity from the grid so they could maintain some of their bare core requirements. But that was because they weren't able to react fast enough to understand that as they were introducing additional distributed power generation concepts into their environments, that they weren't able to understand that if it's going to be a day that has relatively low demand, like a Sunday, that's going to have relatively high generation from our distributed sources like solar and wind, how do we best manage our coal, natural gas, and nuclear assets on the other side so that we don't run into a situation where we have poorly performing prices, such to the point where we're actually paying people to take our products from us. Even the largest company can't survive for long when you are actually paying people to take a particular product or service off of your hands. So in those particular areas, you're going from how do we manage our network? from a bare, let's make sure all the lights are green, we have all those components up and running, but then how do we take the information that we get from sensors, that we get from weather sources, that we get from our projections associated with demand, pull those all together and understand how do we best utilize our assets, and how do we make sure that we don't run into situations where we run a suboptimal pricing model associated with those utilities. So when we take a look at all these particular use cases, we're talking about moving from one area where we were just trying to maintain our particular status quo, if you will. You know, for financial services, we're talking about how do we meet the requirements of our regulators. When we look at retailing, we're talking about how do we meet the supply chain to make sure that we have the appropriate stock on shelves. And in utilities, how do we take a look at power generation and making sure that we have the grid up and running? Those were kind of constraints where we felt there might be this component of the sound barrier before us, that, you know, there was a brick wall that we couldn't break through. And what in-memory processing allows us to do is to flip through those models, either jump over the wall or break through it completely, and say, no, we can, for financial trading, we can take our regulatory requirements, and instead of them being a burden, they can be an asset to us in terms of how do we maintain our competitive advantage in retailing. It can be how do we maximize our pricing and our profits without sacrificing customer satisfaction. And in terms of utilities, we can now tackle some of the problems associated with greenhouse gases and power generation and things of that nature, and utilize these distributed assets such as wind and solar and hydroelectric, bring those all into the component and say, how do we make it that much better as opposed to accepting a particular status quo? But these are all great use cases on different verticals that are associated with maintaining in-memory processing. I'm now going to hand it over to Nikita, and Nikita, you're going to bring us up to speed on how GridGain enables organizations who want to meet these challenges in these particular use cases.
All right. Can you guys hear me? Hopefully.
Yes, sir,
Welcome,
we
everybody.
can.
Perfect. So what I want to basically discuss in the last couple of minutes is to kind of walk you through the evolution of in-memory computing. I think John provided a great overview of some of the business drivers and some of the interesting use cases. So I'm going to give you kind of an overview from a technical perspective how this whole thing evolved. Because we've talked about in-memory computing for the last maybe 35, 40 years. And we really started to talk about in-memory computing as a term somewhere in the mid-'80s. And that was predominantly around the technical use case of caching. And the caching is a very simple concept. Essentially, what we observed quite a few years ago is that we routinely, go from application to database with exactly the same data sets. What if we could keep those data sets in application, in memory, instead of going to database constantly, and we can greatly improve our performance? Because naturally, when you keep something close to application in the same RAM as the application versus going to a remote database, your performance will speed up dramatically. So that was the original use case for memory computing, dating back to the mid-'80s at the very least. Practically every database, every client-server application, we have some form of caching. What we discovered after that is that the RAM of a single computer is just not big enough. And very quickly, we were faced with the problem, how can we distribute that? How can we use multiple computers to keep data inside of the RAM? And that's where complexity really jumped, because all of a sudden we have to face all the distribution problems. How do we keep data intact? What if there's a failure of server? How do we replicate the data? All the myriad of different questions. And that's basically by mid-'90s where the caching really evolved into the distributed caching. And the qualitative jump was pretty high because the type of issues engineers and developers had to deal with were pretty significant. As distributed caching was evolving more and more, we kind of naturally arrived to a point probably by beginning of 2000s where we had a new term called data grids. And data grids essentially were distributed caching on steroids. We accumulate so many different use cases, so many different functional areas, such as transactions, for example, such as read and write through a SQL databases. All this complexity kind of led to formation of in-memory data grids. And that's a kind of underlying technology that we know today. If you look at any in-memory computing products, the term in-memory data grid would be the underlying core technology across all of them. And then around maybe 7 years ago, what happened is that we essentially have this entire explosion of different form and factions in areas of in-memory computing. All of a sudden, we have database options like Oracle or Microsoft SQL have. It's an expensive option. You can buy this option for in Oracle 12c, for example. Then you can insert tables to the memory. Then we have in-memory Hadoop accelerators like Spark, Apache Spark. Then we had a bunch of streaming products where people were basically doing processing to stream data in memory. We have a business analytics in memory. We have a data analytics in memory. We have in memory this, in memory that. In the last literally 4 or 5 years, we have a literal explosion of different applications, products, projects, solutions that somehow involve in memory computing. And that's what created this massive confusion in the market right now. So what we've done at GridGain, essentially we're bringing simplicity back to the memory story. What we've developed essentially is a in-memory data fabric, and I'm going to switch the slide so you can see a little bit bigger picture here. And in-memory data fabric takes a holistic canonical view to in-memory processing. So in-memory fabric slides in between your applications and your data sources. It provides you great scalability at tremendous performance advantages. Always keep remember that in memory itself is anywhere between 500 and 5 million times faster than a spinning disk. So advantages that in-memory computing can bring you can be quite phenomenal. So in-memory fabric really an interesting technology and really addresses quite a few problems. First of all, in-memory data fabric doesn't replace your database. It doesn't require that you replace your database. It's a very painful process when you're adopting in-memory databases of a variety of different vendors. They would typically ask you to remove your existing database and replace it with new one. And it's a pretty hard process because you have invested a lot and you have a lot of data and process around your existing databases. In-memory data fabric works with existing databases. It slides right in between, providing this layer that application can now talk to and will automatically manage data from various data sources, whether it's your traditional OLTP SQL databases, your new NoSQL database and structured data, or even Hadoop. You're going to be able to interact with all that data in memory and gain tremendous performance and scalability benefits. So naturally, in-memory data fabric brings not only that, it has all the features and capability we would expect from enterprise-grade in-memory solution. It has practically unlimited scale-out. One of the largest customers we have runs us on 2,000 nodes in a cluster. It's a pretty large installation. We have tremendously high availability, plenty of ways to manage the failover, manage the geographically distributed data center replication. We have the best security story in the industry when it comes to memory computing. We work with many financial organizations, and we have the complete audit trail of every record, of every touch of the data, which some of you in financial services know how it is important today. Naturally, we have other functionality that basically tailored to the enterprise users as well. But the core technology is open source. It's Apache-based license, and it's Raleigh commodity software and commodity hardware, So it's a great product. It's easy to try because it's open source. You can try on your own pace. And there's a company behind that essentially stands behind this product. So let me give you one example. I mentioned that in-memory computing can really bring tremendous performance. I don't want to bore you with details. Sberbank is one of the largest banks in Europe. I think number 3 bank in Europe. And what we've done is they had a tender, open tender for a software to build a real-time risk and leverage reporting. The long story short, we won this tender. We beat everybody else, like Oracle and TIBCO. But the real interesting fact from this exercise was the sheer performance that these folks from Sberbank really achieved with GridGain. Think about this. They achieved a 1 billion transactions per second. I'm talking about a fully asset financial transactions. And they achieved that on a 10 commodity blades with overall 1 terabyte of RAM with a cost of entire hardware setup less than $25K. So think about this disposition. And 1 billion transactions per second on the one side and $25K worth of hardware on the other side. So that's what makes in-memory computing in such an irresistible proposition, because economics just simply unimaginable today. And when I started in this business over a decade ago with in-memory processing, it was not the case entirely. In-memory was much more complex. There was a lot of economical barriers, and only the big Wall Street companies, or government agency could afford this. Today, literally every startup, every garage level startup, and any company bigger than that can afford in-memory computing, because again, you can get that tremendous performance. You can talk about 1 billion transactions per second, real financial transactions per second, on literally, on hardware that costs less than a new car. So, John, this is, I think, the last slide that I have, and you can probably take it away from me at this point.
Yeah, and I think one of the questions we need to give the people who've been joining us is where can they go from here associated with it? I think from my perspective, speed of response is becoming extremely important. It's not just a technical requirement that has come from IT departments who say, hey, we really want to go real time. It's something that across many different workloads, whether they be operational or analytical, that being able to meet that customer or that speed of response or that expectation of when I hit the key, I'm going to see information come back to me. It's a very important aspect for not just the iteration through those particular workloads, whether you're trying to define the right customer mix or you're trying to find the right operational processing, but I think it goes to the adoption rate where people are going to say, hey, it's not something that's slow, it's something that's very responsive to what we want to do, and we know that when we go to that platform, we can get that information. I think that people need to understand that, as you pointed out quite rightly, processing is not just in database. There are in-memory databases that are out there, but what we're talking about here is in-memory processing, as you said, data fabric, that really allows you to have a lot of flexibility in the way that you implement your system, not to say we have to go down this one particular technology path. A data fabric allows you to go through many different areas. And then the new solutions that come from this are going to be very important. They're going to be the things that break into new revenue-generating areas, new data-based applications that allow us to find that new competitive advantage as opposed to going incrementally. Will allow us to go on a revolutionary thing where we're able to jump from one status quo to something where we've got whole new areas of revenue and competitive advantage that go with that. So those are the thoughts that I think we should share with our guests. And, I think our next step up is where we're going to talk about some of the questions that are coming in. I've seen quite a few of them in the chat window. But, Raleigh, I'll let you take back control and moderate us through a series of questions.
Thank you, John. Before I jump into the questions, I did want to point out these additional resources to our audience. I'll also include these links in the follow-up email that will go out tomorrow. If you have any questions, you can also log them once again in the Q&A panel. You should see that in the right-hand column of your screen. John, let's start with you. This first question is, how is an in-memory data fabric different from other in-memory offerings, such as an in-memory database or in-memory data grid?
Okay. So from an in-memory database perspective, you've got one facility where you're basically talking quite a bit these days about the ability to go to a SQL-based database. We're seeing some improvements in the area of Hadoop associated with in-memory processing associated with Spark. But what you're doing in that particular area is you're limited to one type of domain, whether it be a SQL-based database management system, whether it's a Hadoop-based platform. You're kind of limited in that particular area when you look at that. But whereas when you go to an in-memory fabric, you kind of have the ability to put that in any of the combinations and permutations of your architecture. Nikita, I'll let you kind of give some of the details of it, but I think when you start talking about an in-memory fabric, you're talking about a much more flexible architecture choice that empowers not just one particular silo of information, but the breadth of information in your enterprise.
Right. We think about a memory data fabric as a natural evolution. Instead of basically having a bunch of point solutions, as you mentioned, siloed things. Think about this: when you have 2 or 3, you're already in a world of pain because you have to integrate 3 individual products, potentially 3 different companies with different configuration, different learning curve, different programming APIs, different everything. And that's what we've seen from our customers, that they, as in-memory computing really took hold and is becoming the centerpiece in a lot of different organizations, IT strategies. They try to move away from point solutions because it's essentially just not effective and not efficient to them. And a memory data fabric that combines all the major use cases, from transactional processing to analytical processing to Hadoop integration to streaming processing to high-performance computing, all of those capabilities right there in memory data fabric from GridGain. A lot of IT pros see it basically as a canonical way to introduce memory computing into the data centers, into the, across multiple applications. So, we obviously biased, but we see it as a natural an expansion and natural evolution of memory computing today.
Thank you, Nikita. Staying with you, the next question is, what are the main obstacles to implementing in-memory technology, either technical or business related?
It's a good question. I don't think, if you would ask me this question 2 or 3 years ago, I would say the main obstacle would still be kind of psychological, because people didn't have good understanding of what a memory computing is, what kind of benefits it can bring, what economical challenges would be in the price and cost of the solutions. Most of it is going away. With lots of big companies putting lots of dollars into the marketing of this. People get educated and they have less of these basic questions. So literally what we're seeing today across our customer base, I don't think there's a one single theme that dominates all of it. I think it's a variety of smaller issues, if you will. Sometimes it's essentially figuring out exactly what to get. Because if you go to the market right now, you just type in memory computing in Google, you'll get an avalanche of information. It's very confusing. Because I mentioned to you, there's this explosion, remember my slide, of literally dozens and dozens of different variations of what a memory computing is. So one of the challenges our customers facing initially is, what do I use? What's better for my particular use case? Another challenge, sort of a challenge, there's not really a standard body today that kind of brings standardization to some of the use cases on in-memory computing. There's a small standard, the JCache for Java developers. That's, working in this direction. But really, it's a vendor by vendor, and that's another problem. Some of the other problems could be that in-memory computing may require a certain level of expertise from engineers to introduce that to the company as well. So this is none of these, at least from my perspective, for what I'm hearing from my customer base, none of this is kind of standing out. But those are a laundry list of questions and concerns we're fielding on a daily basis.
Thanks, Nikita. I'm going to jump back over to John. John, we hear a lot about cloud. One of the audience members wants to know, how does this apply to cloud?
Well, I think that, when we start talking about cloud, we can, the implementation avenue that allows for cloud as an implementation avenue allows you to do a lot of things that you may not be able to do otherwise. I think that when we start talking about in-memory processing associated with a cloud architecture, a lot of the platforms that are out that are allowing you to go in that particular area. So I definitely think that you can use this in a cloud implementation environment. I think the main challenge that goes with that is being able to make that bridge from one cloud environment to another associated with the memory space as you scale out to increase the area that you have associated with that. Nikita, I don't know if in particular the GridGain supports going to a cloud-based architecture, whether that would be a private or a public architecture, but I think that one of the big challenges there is going to be how do you manage the memory space so that you can keep everything aligned for the processing environment.
Yeah, I think the whole cloud story is a little bit orthogonal here. It's definitely implementation strategy, not, the cloud is not inclusive or exclusive for memory computing. Essentially, it's kind of orthogonal. I think for us, I can give you statistics for GridGain. I believe about 25 to 30% of our customers run the cloud, predominantly in Amazon public cloud. What can you dial into? What can you glean, from that statistic? I don't know how much. We definitely, as a software, and we are very, easy to use in the cloud environment. That's given. Practically any software today would be. There's no surprise here. But really, a cloud, whether it's a private, which I believe most of our customers use, or whether it's a public infrastructure like Google or Amazon, it's just basically case by case. It's an implementation detail for particular customers, what they want to do.
Thanks, Nikita. Staying with you, there's a product-specific question. Does GridGain's data fabric use a key-value data structure? How does it relate?
Yes, at the core of data fabric is a key-value structure. It's a key-value data store. Key-value data store is one of the most flexible key-value store. So fundamentally, remember I mentioned you in-memory data grid technology. That's what's at the core of data fabric. So the data is stored as a key-value store in the key-value store within the data fabric itself, and then it's exposed in a variety of different forms. You can view as data as SQL data, so you can use SQL to query it. You can view it as a file system. So, for example, you can use Hadoop file system interface to really, view and access the data as a file system. And you can view it as a key-value business store as well. So there's a variety of different shapes and forms how this data get exposed to the user, to the developer. But fundamentally, at the core level of data fabric, it's stored as a key-value store.
Great. Thanks for taking that question, Nikita, and John for taking the other ones. I also wanted to thank our audience for joining us today. As I mentioned at the start of the webinar, you will be receiving a follow-up email from Enterprise Management Associates tomorrow that will include the on-demand playback as well as these resources listed on the slide. So thanks again for joining us, and enjoy the rest of your day.